chemical reactions involve changes in energy. These reactions are giving out energy as light, heat, sound, even electricity. But there isn't an obvious energy change when sodium hydroxide solution is added to sulfuric acid. Take another look, this time using a thermal imaging camera. Hot objects show up as white. As the two reactants are mixed, the beaker immediately gets hotter. Heat energy is being given out by the reaction, causing the temperature of the chemicals and the beaker to rise. An electronic probe measures the temperature change. The reactants start off at 24.4 degrees Celsius. Add them together and the temperature of the reaction mixture quickly rises. Heat energy is being given out, so it's called an exothermic reaction. But not all reactions give out energy. Add barium hydroxide to ammonium thiocyanate and nothing much seems to happen. Look again through a thermal camera. Cool objects appear blue, even black. The reaction is taking in energy from its surroundings. By taking energy from the beaker and the chemicals themselves, the whole thing is cooling down. It's an endothermic reaction. A probe shows how the temperature of the reaction mixture quickly falls. As the two solids react, they become liquid. The temperature falls to below -11 degrees C. But why do these energy changes occur? This balloon contains a mixture of hydrogen and oxygen. Ignite it and the hydrogen and oxygen combine, giving out energy and forming water. The individual atoms in each molecule are held together by chemical bonds. Hydrogen atoms are held together by a single bond. Oxygen atoms are held together by a double bond. When a reaction happens, these bonds are broken and new ones are made. Bond breaking requires energy. But when water molecules form, new bonds are made. Bond making gives out energy. In an exothermic reaction like this, more energy is given out than taken in. So what's happening in this endothermic reaction? One way of measuring the rate of a reaction is to look at how quickly the products are formed. The reaction between hydrochloric acid and sodium thiosulfate produces a suspension of solid sulfur. As more sulfur is produced, the solution becomes cloudy. At some point, the black cross will no longer be visible. It's a simple way of monitoring the rate. The quicker the cross disappears, the quicker the reaction. To measure the rate more accurately, you can shine a light through the solution and use a light meter to measure exactly how much light passes through it. amount of light reaching the meter is already falling. As the sulfur is produced, more light is absorbed by the reaction mixture and less light passes through. The meter reading continues to fall. The reaction is over when the amount of light reaching the meter remains steady. A data logger captures all this information. Attach it to a computer and the results are represented graphically. The amount of through is plotted against time. It produces a curve that eventually levels off when no more light is able to pass through the cloudy sulfur. The concentration of the acid was 1 molar. So what do you think will happen if it's increased to 2 molar? Once again, the data is collected and a graph of light passing through the solution is plotted against time. It's still a curve, but this time the curve is steeper. The sulfur has been produced more rapidly. The rate of the reaction has increased. For a chemical reaction to take place, the reacting particles must collide with each other. On the right, the yellow reactant is doubled and the collision rate increases. Decrease the concentration of hydrochloric acid and what do you think will happen? With this reaction, the initial mixture is at a room temperature of 25 degrees C. It's colourless, but the moment that one of the reactants is used up, it changes to blue-black. It takes just 21 seconds. At 35 degrees C, the reactants are now 10 degrees warmer. What do you think will happen? This time it takes just 11 seconds. When the reactants are now just 15 degrees C, how long will it take? How might increasing or decreasing the temperature be affecting the number of successful collisions? This is hydrogen peroxide. It slowly decomposes to form water and oxygen. Any oxygen produced will be collected in the syringe, but at room temperature the reaction is so slow you'd think nothing was happening. One way of speeding up a reaction is to add a catalyst. Add manganese dioxide and the hydrogen peroxide quickly decomposes, producing oxygen. But is it the best catalyst for the job? To find out which of these catalysts speeds up the decomposition of hydrogen peroxide most effectively, the same mass of each is placed into a measuring cylinder. Iron oxide, lead dioxide, and manganese dioxide are the chemicals under investigation. A small amount of washing up liquid is added to make the production of oxygen more visible. The tube on the left is the control. It contains no catalyst. Finally, in goes the hydrogen peroxide. As oxygen is evolved, the washing up liquid forms a foam which rises up each cylinder. The rate at which the foam is produced is a measure of how effective the catalyst is. Lead oxide is much better than the rest. Specific catalysts are used to speed up specific reactions. Cobalt chloride solution is the catalyst in this next reaction. A catalyst is a chemical that takes part in a reaction but doesn't get used up. Look again at what happens to the colour of the cobalt chloride. At the end of the reaction, the pink cobalt chloride has returned to its original state. So the amount of any catalyst added to a reaction should still be present at the end. For this next reaction, we'll be using 0.25 grams of copper oxide. It acts as a catalyst in the thermal decomposition of potassium chlorate. The tube on the right contains the catalyst, the one on the left doesn't. As the potassium chlorate is heated, it decomposes and gives off oxygen. The quicker the reaction, the sooner the glowing splint in the neck of the tube will relight. The absence of a catalyst makes the decomposition to produce oxygen much slower. Filtration will recover the catalyst from the other tube. The mass of this filter paper is 0.83 grams. Water dissolves away any remaining potassium chlorate. But the black catalyst doesn't dissolve. Once the filter paper has dried, it's re-weighed. Its mass is now 1.07 grams. If the filter paper alone has a mass of 0.83 grams, how much of the catalyst has been recovered?